Hi, we're the Theory Group, and today we're excited to share our findings and insights from the research we conducted in collaboration with the Theory Lab at UMass Amherst. Navigational services such as Google Maps are crucial for people worldwide, and the shortest path problem holds significant importance in network analysis. Fortunately, various algorithms like Dijkstra's have been developed to address this problem, but implementing these algorithms on large systems can be complex.
To address this problem, a researcher named Klein proposed a solution that involved preprocessing the graph and storing only the necessary information needed to compute the shortest distance in a data structure known as a distance oracle. But this algorithm uses dynamic trees, which is a huge problem in practice. Regardless of its maintenance issues, Klein's approach inspired future studies. More recently, researchers devised a recursive algorithm that was simpler yet comparable in efficiency to Klein's implementation. These researchers employed a divide and conquer strategy to preprocess the graph. The first step involves dividing the interval that encompasses all the vertices on the infinite face into two sub-intervals. From the endpoints of each interval, we compute the shortest path tree using Dijkstra's algorithm. Furthermore, we recursively divide the intervals into smaller subgraphs. After computing our shortest path trees, we proceed to two main steps: finding the shared edges between these trees and contracting these edges.
Suppose we have two shortest paths represented by the red and the blue line. The black arrow is the edge that is shared by these two paths. This edge will also be present in all the shortest paths rooted at these green vertices in the interval. We can find multiple shared edges between these shortest paths and save them to further reduce the search space. Here's how the contraction of edges would work. This is a visual representation of how the contraction would look like. Finally, after multiple recursions, this is how each subproblem would look like. From prior figure, let's analyze the space complexity of the algorithm. At every level, the total number of vertices is roughly O of n, because we are recursively contracting from the same graph. Since we are dividing our interval in each recursion, there are O log of h levels, where h is the number of vertices in our interval. Therefore, the space complexity is O n log of h.
This is the representation of how the distance oracle would look like. So, according to Euler formula, the upper bound of this data structure would be 12n minus 24. Now, let's analyze the time complexity of the algorithm. Time complexity is proportional to the time to compute a shortest path tree. So the total time complexity would be n log h, where O n log n is the runtime of Dijkstra's algorithm to compute the shortest path. So, to summarize our finding, let's compare the runtime of the three algorithms we have mentioned thus far: Dijkstra brute force algorithm, Klein MSSP, and our recursive MFSP. As you can see, our MSSP distance oracle are a big improvement from the traditional algorithm with the ease of maintenance.
The runtime and the implementation speed indicates significant practical and undergraduate teaching potential. Based on our research, we recommend some further work to expand upon our findings. We propose implementing the algorithm on a bigger data set to help us assess the algorithm's effectiveness in real-world scenarios and identify any potential limitations. Also, future work could focus on simplifying the underlying concepts to make them more accessible to undergraduate students. Lastly, we would like to extend our gratitude to Professor Hung Lee and mentor Kong Tan from the UMass Theory Lab, and a big thanks to ERSP program and Professor Nina Sota.